I would like to represent how to find prime numbers by new approach. All prime numbers are located on functions y. For n belonging to even numbers, it can be 9n plus 1, 5, or 7. Even numbers are 2, 4, 6, 8, and so on. For n belonging to odd numbers, it can be 9n plus 2, 4, or 8. Odd numbers are like 1, 3, 5, 7, and so on. Y can be a prime number, and n is a positive integer number. Y lies on the axis from 0 to infinity, and from 0 to infinity as well. It means that we can have infinite number of primes. Now, numbers y ending by 0, 2, or 5 should be ruled out, as they are divisible by at least 2 or 5, which proves the number is not a prime. Now, here I put a line in a green, which is y equal 9n plus 5, just to show you that all prime numbers that I placed lies along all of these functions only. I'll show you now examples using these formulas. Let's take 191 number. Let's sum up its digits. It's 1 plus 9 plus 1, it's 11. 1 plus 1, it's 2. Now this number belongs to the function 9n plus 2, where n is 21. As you can see, the rest of this function is equal to the sum up digits of this number, of course reduced to the one digit. 193, as an example, it's 9 times n plus 4, when n is 21. Now sum of the digits, it's 1 plus 9 plus 3, it's 13. 1 plus 3, it's 4. Again, this number equals 4, which is the rest of the function. Now 239, it's 9 times 26 plus 5. Sum up the digits of the number, it's 2 plus 3 plus 9 is equal 14. 1 plus 4, it's 5. Again, 5 is the same as the rest of the function. 241, it's 9 times 26 plus 7. Sum of digits is 7 as well. We can notice here that our n number is our even number, our rest is odd number. It means that this is the prime. At least there's a good chance for it. The same for other ones. This is, for example, odd number, and this is even number. The rule also generates fake prime numbers, but don't worry about that. The amount of numbers that needs to be checked if they are prime is reduced, because we already know they are located at represented functions y. As you can see here, there are not many of them that we need to check comparing to all infinite amount of it. Now let's take, for example, number 113. This belongs to the function 9 times n plus 5, and of course sum of digits gives 5. So we know it is a prime. The same for 1013. It's 9 times 112 plus 5. 1 plus 0 plus 1 plus 3 is 5. Again the same. Now take, for example, 10,013. It is 9 times 1112 plus 5, and the rest is 5, and sum of digits it's 5 as well. But this number is a composite number of 17, 19, and 31. What we know about them? These are primes as well. So we know that we can find some composite number that our mysterious number that we would like to check it as a prime is divided by. A correlation was found between these fake prime numbers and their composite numbers in that way. The correlation between fake prime numbers belonging to function y and their composite numbers, which are also primes, can be shown here. We already know that 10,013, it's 9 times 1112 plus 5, where 5 is the rest, and sum of its digits is 5. Now, the composite numbers also can be shown as our functions y. For 17, it's 9 times n plus 8, where n is 1. For 19, it's 9 times 2 plus 1. 31, it's 9 times 3 plus 4. If we will multiply rests of these composite numbers, we'll get 32. 3 plus 2, it's 5. 5, it's exactly the same number as the rest of our function and sum of digits of our numbers, and it's always like that with the composite numbers. This is the correlation that can be found for fake prime numbers or composite numbers. As you can see on the diagram here, I placed all prime and composite numbers up to 450. That lies on our functions y. As you can see, there's not many of them comparing to all numbers that goes to infinity. It means that there's not many to check, to confirm if they are primes or not. Let's take, for example, that you imagine some number that would you like to check if it's a prime. Let's take 6-digit ones. 503, 317. Sum up its digit number, give us 19. Then 1 plus 9 is give us 10. 1 plus 0 is 1. 1 is our rest and it match function y is equal 9n plus 1. Now, from our mysterious number, let's reduce it by this one. It gives us 503, 316. Let's divide this number by 9 and we get 55924. 4 is our even number and 1 is our odd number. So we can assume it is our prime number. At least it is a possibility. Now we have to check if we can find number n that match one of its function that can divide our mysterious number. In this case, we couldn't find any. It means it is a prime. Let's take other example. 801, 340. As you can see, 0 is at the end, and we already know it's not a prime because it can be divisible by 2, 5, or 10, for example. But it's about the rule how it works. Let's sum up its digits. It's 8 plus 0 plus 1 plus 3 plus 4 plus 0. It gives 16. 1 plus 6 is 7 is our rest. It match function y equal 9n plus 7. Let's reduce our number by 7. We've got 801, 333. Divided by 9, we've got 89,037. 7 is our odd number, and the rest of our function is 7 as well. It means this is not a prime based on our rules. The number is not prime as we have to have rest as odd numbers and quotient even number, and vice versa, rest to be even number and quotient odd number. Let's take other numbers as an example, also 6-digit ones. We've got 823, 553. Sum of its digits, 8 plus 2 plus 3 plus 5 plus 5 plus 3 gives 26. 2 plus 6 is 8, it match function 9n plus 8. Now take off from this number 8 and we get 8 to 3, 545. Divided by 9 and we get 91505. This is our odd number, this is our even number. There is a chance that this number is a prime. We can try to find n match this function if it will divide our number. Unfortunately, none were found, and this is the prime. Of course, you need to remember that divisibility by n matching this function needs to give an integer number as well. Now let's take number 314, 729. 3 plus 1 plus 4 plus 7 plus 2 plus 9 is 26. 2 plus 6 is 8. It match function 9n plus 8 as well. Now take off 8 from our main mysterious number. We get 314721. Divided by 9, we've got 34969. 9 is our odd number and 8 is our even number. There is a chance it is a prime. Now let's check if we can find n matching one of this function that can divide our mysterious number to one of integer numbers. Of course, two of numbers were found. This is 347 and 907. Both of them are primes as well. 347 belong to function 9n plus 5 and 907 to 9n plus 7. For 347, we would have to do 38 iterations to find this number. So to be honest with you, as for a 6-digit number, this is not that much. Or 100 if you will choose this function to find some number that we can divide our mysterious number. Of course, this is not the prime, but following the correlation, if we will multiply rests of this function 5 times 7, we got 35. 3 plus 5 gives us 8, and it matches the same as a sum up of the digits of our mysterious number. As I show in this video, it's quite easy to implement this method. You can make prime checks manually, or if you need a large number and you are a good IT person, you can make a program script. This method also proves that we can have infinite number of primes. It also shows why some primes are very close to each other with a difference of two numbers like 11, 13, 17, 19. Thank you for your time, and I hope you can find even more interesting correlation for prime numbers Bye!